Hi, I'm Adam Beer from Rockfield, and today I'll be presenting stress shadow impact on fracture growth and geometry. Induced hydraulic fractures, as many of us know, follow complicated paths. There's different aspects can contribute to this complexity, including stress shadowing, interactions, branching, choking, curving, and swarms, as well as many other different influences. Two demonstration cases I've got on the screen here is a lab scale type test here on the left hand side, and this is really demonstrating from the well and the perforations how complex the fracture propagation can be. You're seeing splitting of a single fracture here. It's growing in different orientations. Some of the fractures are almost inhibited from further growth and you're getting some dominant ones. Quite a complex pattern you can see there. On the right hand side then, this is one of our models that we've run, and I'll be showing this more in later slides, but this is just a sneak preview showing how there's this cyclic behavior from one fracture to its neighboring fracture, how they're growing slightly different orientations, and you're getting very much an asymmetric growth of most of the fractures. What ends up being resulting is this kind of petal shape fracture sets that you can see in the bottom right hand plot there. Just looking at other lab scale tests that have been done and the fracture propagation from them, this is a nice example that was conducted in 1995, and what we're really looking at is those two figures on the right hand side there and how the fractures are growing quite differently, or actually being not growing at all, very much inhibited. So on figure C, the top right one, you can see that the end clusters are predominantly growing, and they're growing asymmetrically, one of them upwards in this orientation, one of them downwards. And in between there, the fractures are inhibited from growing virtually at all. So this is clearly seen from lab scale tests. But also looking at the field scale, you can see that on this left-hand plot there, which is diagnostics into where the produced gas is formed from, you can see that there's three main clusters. Now these are three stages that have been propagated, each with multi-clusters, but there's three clusters, one from each stage, which are producing 70% of the gas, and 50% of the perforations are producing next to nothing. Many things can contribute to this, but also we're suggesting stress shadowing can be a high contributing factor. On the right hand side then, more field scale observations from multi-stages. Each one of these stages from 1 to 11 are conducted in sequence, and you can see there's a cyclic nature here between 1 and 5 and then 6 and 11, where the fracture is growing slightly further in each case and then almost being reset at stage 6 and then again growing further. So each fracture is in effect trying to grow into an area of less disturbance from its prior fracture stage or fracture stages. Another example to see the influence and the extent of stress shadows that may be formed. In this particular case here, there is a current stage in this area here. It has been propagated where x-axis is time, as you can see here. So from this point here, this is when the fracturing is started. It's propagated all the way to shut in at that time there. These large blue areas during the fracture propagation are areas of stress shadowing, compressive stress shadowing, where the rock is either side of the fractures in the current stage. The rock is being pressed away to accommodate the opening of the fractures of the current stage. Once shut-in has occurred, the fractures are closing again then. So there's relaxation, which is the hot red colours that you can see here. But what I want to draw your attention to is if you look at the length of the fracture there, you can see how far the fracture stress shadows actually propagate, almost to the end of this monitoring well extent there. It's a huge extent, so if it's extending that far away from the current stage, there's a lot of stress shadow impact within the current stage, so influencing one fracture to its neighbouring fracture. Stress shadows have been known for a long time, and analytically they're represented by semi-analytical solutions, assuming penny-shaped fractures in most cases, and generally this is determined based on the fracture half length, the stress that's in the fracture or pressure within the fracture, and then the distance between clusters. And almost there's a scaling effect in between these distances between the fractures, so one fracture neighbouring another one will just be represented as having a smaller half length. But maybe that's just telling half the story. And as we are in an age of very powerful computing, numerical modeling have really taken on this challenge and looking at hydraulic fractures. There's some work done on the left-hand side there by Imperial, which again is showing this petal shape of these multi-cluster stage development where they're growing in areas of less perturbed stress state. In the right hand side then you can see more models conducted by ourselves. The top one there is looking very near well bore fracture propagation, so we've got the perforations in place. Two main fractures are generated from this complex perforation pattern, and in between you've almost got a longitudinal fracture propagating not in the orientation of the in situ stresses where you'd expect it to be growing, which is transverse to the well, but it's growing longitudinal. Now that's because the stress state by those two dominant fractures has been changed because of the stress shadowing effects, and actually allowed that central joining fracture, if you like, to propagate in a different direction. So quite a complex fracture pattern there, almost like an H fracture pattern there, with two key fractures developing from the ends of the perforation pattern. The bottom right hand side there, just another example of multi-cluster models and stress shadowing, asymmetric fracture growth. We'll see some of those again shortly. So the modelling work that's been conducted for this presentation has been done using the Elvin software. This is Rockfield's Elvin software, and considers everything of the geomechanics of the situation. So the in situ stresses, the evolving stress state within the formation, the evolving fracture growth and how that influences the stresses and then influences other fractures. So there's elasticity, yield parameters within the rock, and we also represent the fracture fluid flow within the induced fracture. Very, very simple to set up these models, and they run very efficiently. There's some model details here of one of the key models that I'll be demonstrating. Just in short, this is very much field scale subsurface representations in terms of Young's modulus, tensile strength 7 MPa. The stresses that we have here between 50 and 40 MPa, pore pressure 30 MPa. We're injecting slick water at 15 barrels a minute for a single fracture here, up to 1250 barrels. So within the modelling, when geomechanics is taken into account, there's certain criteria that's required for the fracture to be inserted and to propagate. First of all, it must generate a stress, tensile stress intensity at the tip of the fracture, so converting from its natural compressive state to a tensile state, and therefore overcome the formation tensile strength. So there's a lot of work that needs to be done in the end. It overcomes the minimum total principal stress in terms of pore pressure and the formation matrix stress and this tensile stress as well. What it does is that generates a lot of compressive stresses in areas where the fracture has already propagated. So you can see in the plot here on the bottom right hand side, you can see compressive regions, the cold colors, the blue colors. You can see that these are propagating out quite an extent, similar to what we saw before from the field measurements. And this is all compressive, very close to the fracture, and then dying out. There's a few controls on that, which we'll cover shortly. Then at the fracture tip, you get this stress intensity, and this is turning from the compressive natural stress state all the way to tensile to actually break the rock at the fracture tip. Once that happens, we actually insert the fracture. So we don't insert a fracture until it actually overcomes that tensile strength. I mentioned a few controls on the stress shadow area. One of them is elastic modulus. So I've just got this one example of two Young's modulus. On the left hand side, we're looking at 32 gigapascals. On the center there, or right hand side, we're looking at 16 gigapascals. Now these both cases have been injected the same amount of volume. Obviously for the 16 gigapascals, because it's a softer formation, you're getting a wider aperture growing and the fracture extent isn't as far. Also, the stress intensity at the fracture tip is more dispersed in the 16 gigapascal case compared to the 32 gigapascal case. Looking at both these cases, the injection pressure itself is very similar between these cases. One of the reasons for that is the injection pressure has to overcome the in situ stress state and the tensile strength of the fracture tip. Those are the two key things it's overcoming, and that hasn't changed between these two models. So the demand in terms of pressure is the same for these. However, For the reasons I just mentioned before, the fracture area is quite different between these models here, with a shorter fracture area of 16 gigapascals because it's got a wider aperture. When we're looking at the stress shadow area then, out of these two models, you can see that the 32 gigapascals is a higher stress increase as you go away from the fracture. So this is the stress shadowing impact. The dashed line here is the in situ stress state, and you can see in both cases it's elevated adjacent to the fracture. We're looking at this dashed line here, but more so with 32 gigapascals, again because it's a stiffer formation, so it attracts more stress. What does this mean to actual heterogeneity in the field? Well, we've done a few models before where we look at fracture height growth. It's a very, very important question. So looking at that in this particular case, we've got significant heterogeneity in the elasticity, which you can see on the left-hand side there, and then the fracture growth is on the right-hand side. You can see how the stress shadow, as it propagates out, and we're plotting the minimum principal effective stress here, how it's different in different stiffnesses of the formation as it's propagating. This then helps drive the fracture either up or down and gives a good indication of fracture height growth. Now, we've looked at a single fracture. I just need to cover this very, very quickly when we look at a multi-cluster situation. To allow multi-clusters to propagate, and what we've had to do for this modelling is to take into account perforation pressure drops. So this is your limited entry perforation pressure drop. It's the reason why perforations are limited in number and the diameter of those is carefully controlled. This is something I'm sure you're all quite aware of, and the purpose of having these perforations, number of perforations, is to try and penalise any fractures that are taking all of the flow and allow a more even distribution of the fractures. So just as a demonstration of this, we've got some models set up here. This is no perforation pressure growth on the left, and then on the right we've put in the perforation pressure growth. You can see, as I set off the animations here, where there's no perforation pressure drop, you're getting a dominant fracture propagating. And the other two fractures are pretty much shut in. Generally that's due to stress shadowing. You don't need much stress shadowing, and this one will take everything. However, putting in a sensible range of perforations, 6 perforations, 7.62 diameter, and a discharge coefficient of 0.78, you can see suddenly the fractures are growing far more even in this case. Again, something to note, when we're looking down the length of the well, you can see that there's this petal effect even of 3 fractures growing, and they're growing quite asymmetrically. I'll cover that in the next few slides. So this is a section through the model where I've tried to demonstrate the stresses within the formation between the fractures. So really the stress shadow region. As you remember from previous slides, blue is the cold colours are compressive, red colours are tensile. You can see there's a significant impact of stress shadow in this case. If we just look at this in a little bit more detail in the very early propagation of the fractures, cold colours again are compressive, so you can see that these two outer fractures are almost merging in one area and creating a large region of compressive stress there, whereas the central fracture is propagating compressive stresses predominantly in these directions here. What these are doing, what all these compressive stresses are doing, is limiting the fracture growth of other fractures in this direction. So these two are combining to stop the central fracture growing that direction, and the central fracture is limiting the growth of these in this direction. If it's limiting growth in one direction, the fractures have only got one direction to grow in the opposite formation there. So you can see one-way propagation in those two directions. This really starts to describe the pattern of fractures that we're seeing and the asymmetric fracture growth. When we look at it in an 11 cluster case, this is 6 meter spacing, injected at 80 barrels a minute. The size of the domain, 250 by 250 by 100 meters deep. When we look at these fracture growths here, you can see they start off, the end fractures start growing faster, but when the injection rate is increased, you get the perforation limited entry kicking in, all of the fractures start growing, and you're starting to get this real petal shape here as they're propagating out. Each fracture wants to keep growing, but it wants to grow in the path of least resistance, and that's not necessarily close to its neighbor, it's sometimes further away. Observations of this, what do we get? We get this cyclic behaviour. What is the half length of these fractures that are growing? How does it affect height growth of the fractures? There's many questions in the distribution of these fractures and how they influence and implications to frac hits, height growth, stimulated reservoir volume, and also proppant placement. So the timing of that fracture growth and where the proppant is injected is very, very important. Further applications of such modelling include input for completion design, cluster and stage spacing, well spacing itself. Looking at near wellbore fracture stress shadowing as shown on the right there and previously presented. There's a question of injection fluid and viscosity effects. Higher viscous injection fluids, how does that affect stress shadowing and the propagation of the fractures? Proppant placement as well, looking at where that is placed within each fracture, and then 3D heterogeneity. These are just some examples. That brings me to the end of the presentation, so thank you very much for giving me this opportunity to present.